Let us solve a question on utility maximization with three goods. The question is, suppose an agent consumes three goods, that is x, y and z. Her utility function is being given as u is equal to under root x plus under root y plus under root z. The agent has an income of m is equal to $1. Suppose the prices of goods are, price of good x is $1, price of good y is $1 and price of good z is $1. We have to solve for agent's optimal consumption. Okay, so what we are being given, the utility function, and let's write it here, u and our, and let me write it here. What we want to do, we want to find the optimal consumption. That means we want to maximize utility. So our question will be like this: we want to maximize the utility of the consumer, which is equal to under root x plus under root y plus under root z, subject to the budget constraint. And what will be the budget constraint here? That is very simple. Budget constraint will be the price of x times units of x consumed plus price of y times units of good y consumed plus price of z times units of z good consumed should be equal to the income of the consumer. That implies price of x, price of y and price of z are all equal to 1. So can I write it here? X plus y plus z should be equal to, the agent's income is also being given as equal to 1 here. Okay, now to solve this we apply the Lagrangian method here. Okay, so first we need to set this, to solve by using Lagrange's multiplier method. First we set this budget constraint equal to 0. That implies 1 minus x minus y minus z is equal to 0. First step is this. The second step will be to multiply this resulting constraint with lambda. Okay, I will write it like this. So here lambda times 0 will be 0 on the RHS. Then we can find, or rather form, the Lagrange's function. Lagrange's function will be the aggregate of this resulting constraint plus the given utility function. That is, we add the objective function and resulting constraint. So what is our utility function? That is equal to under root x, and I can write it as x raised power 1 upon 2 plus y raised power 1 upon 2 plus z raised power 1 upon 2. To this we add this resulting constraint that we formed. That is equal to, that is lambda times 1 minus x minus y minus z. Okay, this is our Lagrange's function. Now to find out the optimal consumption bundle, what will we do? We partially differentiate this Lagrange's function with respect to x, y and z, set them equal to 0 and solve them simultaneously. So first we take the partial derivative with respect to x. L subscript x means the partial derivative of this function with respect to x. Okay, so derivative of x raised power 1 upon 2 by power function rule, 1 upon 2 will become coefficient 1 upon 2 and exponent is subtracted by 1. So 1 upon 2 minus 1, it will become minus 1 upon 2. Since we are taking the partials, since no x is involved in the second term and in the third term, their derivative will be equal to 0. And here we have this minus x. So the derivative of minus lambda x will be equal to minus lambda. So I can write minus lambda and I set it equal to 0. Symmetrically, L subscript y means the partial derivative of this Lagrange's function with respect to y. So we are interested with this variable here. Again, its derivative is 1 upon 2 y raised power minus 1 upon 2 minus derivative of y in this will be minus 1. So minus 1 into lambda is minus lambda and we set it equal to 0. Likewise, L subscript z will be equal to 1 upon 2 z raised power minus 1 upon 2 minus lambda is equal to 0. Can I rewrite it in this fashion? That is 1 upon 2 under root x is equal to lambda. And similarly, can I write it in this fashion? 1 upon 2 under root y is equal to lambda. And can I rewrite this as 1 upon 2 under root z is equal to lambda? Why? Simply I transposed x raised power minus 1 upon 2 to the denominator. Exponent sign changes. If it is minus 1 upon 2, it becomes plus 1 upon 2. And likewise, I have done this. Here you can see, since let us say equation 1, this is equation 2nd, this is equation 3rd here. Okay, since the RHS of the three equations are same, we can equate the LHS of these three equations. That implies from 1, 2 and 3 we will get 1 upon 2 under root x is equal to 1 upon 2 under root y, which is equal to 1 upon 2 under root z. So multiplying both sides by 2, so multiplying 2 here, here and here, this 2 gets cancelled in each of these terms. So we are left with 1 upon under root x is equal to 1 upon under root y is equal to 1 upon under root z. Reciprocating each term, so we will get under root x is equal to under root y is equal to under root z. Can I write it in this fashion? If under root x is equal to under root y, squaring both sides, so if I square it here and here, so square and root gets cancelled here, so x is equal to y. Similarly, when under root x is equal to under root z here, so squaring again, square root gets cancelled, so we are left with x is also equal to z. Simply plug the value of x and y into the budget constraint. The value of x is equal to y and x is equal to z into the budget constraint. In this budget constraint, that means we have first x, so we have x plus y is equal to x, so in place of y I write again x plus y, z is equal to x, so in place of z I write again x is equal to 1, which implies 3x is equal to 1 implies x will be equal to 1 upon 3. If x is equal to 1 upon 3, since x is equal to y, that implies y will be also equal to 1 upon 3, and since x is equal to z, that implies z is also equal to 1 upon 3. So these are the optimal consumption bundle that the given agent should consume given his utility function and the budget constraint. I hope I make myself clear in this video. Thank you.